Hello friends, I am Dr. Sirajul Akfaizi. I welcome you in my YouTube channel. Today in this video, we are going to learn about carbohydrate structure. You know friend, carbohydrates are organic molecule found in nature, constituting one of the four major classes of biomolecules. The other three are proteins, nucleic acid and lipids. Saccharide, saccharo is Greek for sugar. Now, carbohydrates are aldehyde or ketone compounds with multiple hydroxyl groups. The basic molecular formula is like that, where N is equal to 3 or 4 or 5 or more. The term carbohydrates comes from the observation that when you heat sugar, you can get carbon and water, hence hydrate of carbon. You can see in this picture. Now classifications. They are classified according to the number of structural unit. Monosaccharide, they are the simplest carbohydrate that cannot be hydrolyzed into simpler unit. Disaccharide produce 2 molecules of monosaccharide on hydrolysis. Oligosaccharide produce 3 to 10 monosaccharide unit on hydrolysis. And polysaccharide produces more than 10 monosaccharide unit on hydrolysis. So, monosaccharides, they are the simplest carbohydrate unites which cannot be hydrolyzed to simpler form. General formula CH2O in N is equal to or greater than 3. According to active group in sugar, if monosaccharide contains aldehyde group, it is called aldose, and if contains keto group, it called ketose. Now according to the number of carbon atom, if sugar contains 3 carbon, it's called triose. 4 carbon, it calls tetrose. 5 carbon, pentose. 6 carbon, hexose. 7 carbon, heptose. So triose example, glyceraldehyde. Tetrose example, erythrose. Pentose example, ribose. Hexose example, glucose and fructose. So by combining two methods, we find that 3 carbon aldotriose, ketotriose, aldotetrose, ketotetrose, aldopentose, ketopentose, and aldohexose, ketohexose. So 3 carbon diglyceraldehyde, dihydroxyacetone, and 4 carbon deerythrose and deerythrolose. So 5 carbon deribose, deribulose, and dexylose, dexylulose, D-glucose, D-fructose. The structure of glucose can be represented in one of the following ways. The straight chain, open chain structure formula. Aldohexose can account for some of the properties of glucose but cannot experience some reaction, D-glucose. The cyclic structure accounts for the remainder of the chemical properties of glucose. This cyclic structure can be represented in two forms. Fischer projection formula, where the aldehyde group react with an alcohol group on the same sugar to form hemiacetal. So you can see alpha D glucopyranose or beta D glucopyranose. Haworth formula, where the cyclic structure is represented in pyranose 6 member and furanose 5 member, ring resembling pyrene and furan. Here OH and H written above and below instead of right and left. Above and below instead of right and left. So what is on right, below, left, above? Right, below, just right, RB, right below, LA, left, above, except last carbon which close the ring, in which left below, right above. left below, right above. So pyrene, furan, alpha D, glycopyranose. Now hemiacetal or hemiketone. Aldehyde alcohol, hemiacetal, ketone alcohol, hemiketone. An aldehyde or ketone can react with an alcohol in a 1:1 ratio to yield hemiacetal or hemiketone respectively, creating a new chiral center at the carbonyl carbon. Now both N-chair form represent the three-dimensional configuration of sugar in nature. So fructose in open chain and Howard forms. D-fructose, alpha D-fructofuranose, beta D-fructofuranose. Now friend, anomeric carbon, asymmetric carbon atom, chiral carbon. It is the carbon atom attached to 4 different group of it. The formation of ring result in the creations of anomeric carbon at carbon 1 of aldose and at carbon 2 of ketose. So alpha D glucose you can see, and D fructose you can see, alpha D fructofuranose. Now reducing sugar. If the oxygen on the anomeric of carbon, the carbonyl group of a sugar is not attached to any other structure, that sugar is a reducing sugar. Only the state of the oxygen on the anomeric carbon determines if the sugar is reducing or not. The other hydroxyl group on the molecules are not involved. So sucrose, lactose, maltose. A reducing sugar can react with chemical reagent, for example, Benedict solution, and reduce the reactive component with the anomeric carbon becoming oxidized. So the compound having one or more asymmetric carbon atom shows two properties: optical activity and stereoisomers. So what is optical activity? It is the ability of compound to rotate plane polarized light to the right or to the left. If the compound rotate plane polarized light to the right, it is called dextrorotatory or D or positive. If it is rotate plane polarized light to the left, it is called levorotatory L or minus. So direction of rotation is independent of stereochemistry of the sugar, so it may be designated D minus, D plus, L minus, L plus. For example, the naturally occurring form of fructose is the D minus isomers. Dextrorotatory sugar D or plus, glucose, lactose and starch. Levorotatory sugar L or minus, fructose and invert sugar. Now friend, stereoisomerism. Compounds that have the same structure formula but different in a special configuration are known as stereoisomers, and phenomenon is called stereoisomers. The number of possible isomers of compound depends on the number of asymmetric carbon atom and is equal to 2 to the power n. Glucose with 4 asymmetric carbon atom has 16 isomers. The more important types of isomer include D and L isomers, pyranose and furanose ring structure, alpha and beta anomers, Isomers and Aldose-ketose isomers. Isomers are compounds which have the same molecular weight, same percentage composition, and differ in their physical and chemical properties. Stereoisomers are compounds that have the same structure formula but differ in a special configuration, arrangement of atom and group of atom in a space around the asymmetric carbon, different configuration. So you can see D and L isomers in enantiomers. So monosaccharide is designed D if the hydroxyl group on the highest number asymmetric carbon. Pre-list carbon is drawn to the right and D is glyceraldehyde, and FL hydroxyl group on the highest number asymmetric carbon is drawn to the left and is L-glyceraldehyde. You can see in this picture. So D glucose and L glucose. The majority of sugar in human are D sugar. Two exceptions are L-fucose, a glycoprotein, and L-iduronic acid. You can see L-glucose and D-glucose. Pyranose and furanose ring structure. Monosaccharide are either pyrene, 6-member ring, or furan, a 5-member ring. The glucose in solution more than 99% in the pyranose ring. Now alpha-beta anomers. The ring structure of aldose is hemiacetal, since it is formed by the combination of aldehyde and alcohol group. Similarly, the ring structure of ketose is hemiacetal. The cyclic structure is retained in solution, but isomerism occurs about position 1. The carbonyl or anomeric carbon atom to give a mixture of alpha glucopyranose and beta glucopyranose. So a cyclic alpha beta anomers of sugar in solution are in equilibrium with each other and can be spontaneously interconverted. Processes called mutarotation. Now friend, epimers. Isomers differ as a result of variation in configuration of OH and H on carbon atom 2, 3 and 4 of glucose are known as epimers. Biologically, the most important epimers of mannose and glucose formed by glucose epimerization at carbon 2 and 4 respectively. So epimers of glucose you can see. Aldose-ketose isomerism. Fructose has the same molecular formula as glucose but differ in the structural formula. Since there is a keto group in position 2, the anomeric carbon of fructose where there is a aldehyde groups in position 1, the anomeric carbon of glucose. So many monosaccharides are physiologically important. Pentoses, ribose, hexoses, glucose, 7-carbon sugar are formed as a metabolic intermediate in pentose phosphate pathway. Carboxylic acid derivative of glucose are important, including D-glucuronate and L-iduronate and gluconate. So sugar were found and biochemical importance. D-ribose nucleic acid, ribulose formed in metabolic process. D-arabinose, gum arabic, plum and cherry gums. D-xylose, wood gums, proteoglycans and glycosaminoglycans. And D-lysose, heart muscles. L-xylose, intermediate in uronic acid path. So D-glucose fruit juices, D-fructose fruit juices, honey, hydrolysis of cane sugar and of inulin, and D-galactose, hydrolysis of lactose, and D-mannose, hydrolysis of plant mayonnaise and gums. Derived sugar. Deoxysugar, lack of oxygen atom. Deoxysugar are those in which a hydroxyl group has been replaced by hydrogen. So deoxyribose in DNA. Amino sugar are compound in which OH at carbon 2 is replaced by NH2. Sugar acid produced by oxidation of carbonyl carbon of carboxylic acid. So you see the aldonic acid, the glucuronic acid, and alderic acid, the glutaric acid. Now friend, glycoside formation. In hemiacetal hemiacetal forms, a monosaccharide can react with alcohol to form acetal and ketal structure called glycosides. And the new carbon-oxygen bond is called glycosidic linkage. Glycoside acetal, the OH anomeric carbon of monosaccharide can react with either nitrogen of amines. The anomeric carbon or atom of sugar can be linked to the nitrogen atom of amine and glycosidic bond. So OH of ribose linked to nitrogen of nitrogenous base to form nucleotides. Now 2OH of other compound may be carbohydrate, may be non-carbohydrate. So ON glycosides. If the group on the non-carbohydrate molecules to which the sugar is attached is on OH group, the structure is an O glycoside. If all sugar glycosidic bond are O type linkage, you can see alpha 1,4 linkage in starch. If the group is an NH2, the structure is N glycosides. You can see. Naming glycosidic bond. Glycosidic bond between sugars are named. So friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel and thanks for watching.